captions on? They do?
Yeah.
Okay, perfect. I have to push an additional button to do it, but I can turn the captions on. I have to do it before I start recording though. All right, so let's get started. This is where we were. This is actually printed from last class. I reprinted the slides out to make sure that I covered this. Applying Hess's law when delta HC is given. So before we go on, what is delta HC? It's, again, I know it's been a week and a half. We studied for that quarterly. That's all you did last week.
Delta,
What is delta HC?
enthalpy change of combustion.
Yeah, delta HC is enthalpy change of combustion. And combustion reactions are generally CXHY plus O2 goes to
CO2 plus H2O.
CO2 plus H2O. We learned last class that an enthalpy of combustion could be any element that we're oxidizing, actually. And so it included, if I just take carbon and I react it with oxygen, and what does that make? CO2. This is technically an enthalpy of combustion. You may want to write that down, because it's going to help us understand what's going on and what we're going to be doing. If I have hydrogen, how does hydrogen naturally exist? And I react that with O2, and I make water, isn't that also an enthalpy of combustion? So the components of the products, carbon dioxide and water, also are delta HCs. When you combust carbon, you make carbon dioxide, you combust hydrogen, and make water. Yes, go ahead. And so why this is important is because we are going to now look at how to create an enthalpy cycle, or an enthalpy of combustion. How does that relate to an enthalpy of reaction? And so take a look at this, and let's go ahead and write out, this is the simple energy cycle I had taught you before. How do we do this if this is an enthalpy of combustion? If we have any random fuel that we are combusting, what does any random fuel formula look like again? What would my reactions actually be? CXHY plus O2. And in a standard combustion reaction, what are my products? Just a standard combustion, not an incomplete. It is carbon dioxide and water. In a combustion reaction, what are the elements that make up a combustion reaction? What are the elements? And what are their standard states? What are the elements of a combustion reaction? Carbon, monatomic, hydrogen, diatomic. Do you agree with me? And oxygen also diatomic. So far following me? Reactants, products, elements in their standard state. Now draw the arrows. What does this arrow represent? Elements in their standard state to the reactant. The O2s are the same, so take it out. What does that mean? This goes to that. Elements in their standard state go to a compound. We call that the delta H F, the formation of that compound. Or these two form to make that. If carbon becomes CO2, what is that called? Carbon specifically becoming CO2, what would we call that? I just said it. Carbon would have to react with what to become CO2? So that makes it a delta H. Hydrogen to become water, what happens? It also has to be combusted. So it's another delta H. And then the overall reaction you could call a delta HI. the enthalpy of reaction for any combustion. And so you're going to want to write this down because we're going to be doing math and these letters are going to be utilized and we wanted to try to make as much sense as possible. One of the things that's confusing about this is that delta HR, delta HF, and delta HC can be used interchangeably, if you'll recall. If I'm talking about this is my overall reaction, I want to call it a delta HR. If I'm specifically combusting something, I can either call it a delta HC or a delta HR. And if I'm forming a compound from elements in their standard state, I call that a delta HF. So just write this down for now and let's take a look at the question and see how this is going to come in handy for us. And we'll come back to this slide. Again, what Cambridge calls a simple energy cycle. So let's take a look at question. And I gave a full slide just to give you a heads up to solve, because this takes up all the space almost. Enthalpy changes of combustion. First question, checkup 9A. Checkup means it comes from the textbook. Question is, write the balanced chemical reaction for the combustion of C2H5OH liquid. That's ethanol, right? So we have space to do that here. What is the balanced chemical reaction for C2H5OH? How do we combust it? What do we react it with? Something that, out of all reactions, who reacts with this with to combust it? Fuel plus oxygen, right? So plus O2. Are you expected to know that? And are you expected to know the products? What are the products of combustion? So CO2 and H2O. So far, so good? What have I not been specifically that asking you to do? Balance the equation. So I need 2 carbons. I need 3 waters. How many oxygens do I have right now? On the product side, 4 plus 3 is 7. What has to go in front of O2 here? Yeah. Because 3 times 2 is 6, but there's another one there. 6 plus 1 is 7. What is 3? Can there be a mark with this? Sure. Now here's the new thing. 9b. It says apply Hess's law to calculate a value for the enthalpy of formation. Just to recall, that means to form that compound from elements in the standard state using the following data. Delta HC of carbon is negative 393.5. Delta HC of hydrogen is negative 285.5, and delta H of reaction is negative 1367.3. So let's go back. Welcome back to our energy cycle and see if we can plug this data in. What is the overall reaction? Yes. This, right? So would these be my reactants and these be my products in forming a cycle? Yes. So let's form a cycle so that we understand how to solve. First, we're going to start with the reactant. Basically, copy paste what you wrote here. Copy C2H5OH plus 3O2, right? Paste. These are my reactants and these are my products. Does that make sense so far? For the top part, it's just reactants go to products. My products being 2CO2 plus 3H2O. What's the part at the bottom? Elements. So here's where you're going to want to be careful. When you provide the elements, make sure you have a balanced equation. So however many carbons you say are here, and however many carbons you say are here, you're going to have the same amount of carbons here. This has to be balanced as well. So how many carbons? What's my first element? Carbon. How many do I have? 2 2 on this side, 2 on this side, that's still 2. It should be 2 on all sides, just to be clear. So this is going to be 2B. With that part, writing the element down. Hydrogen.
8, 6.
But how would I write
3H2.
hydrogen? 3H2, right? Standard state. And what's my final element here?
O2.
O2.
3O2, right?
And the amount would be, it's 7, right? So how do I get a 7 here? 3.5. It technically doesn't matter because the oxygen is going to rid of anyway. 3.5. Okay, next. Write your other arrows. The arrows always go up. So an arrow from here to here. What does this change describe? Elements in their standard state to this compound called ethanol. Remember, the oxygen is actually canceled. Elements in their standard state to the compound ethanol. What would we call that? Out of the data that's being given here or asked for, what do you think that sounds most like? Elements in their standard state to a compound that is made up of those elements. We would call that the enthalpy of formation. Because we're forming from these elements to that compound, we're forming that compound. This is called delta HF. Memorize it, it's always delta HF this way. This arrow right here is the reaction we're studying. What do we call that?
Delta HR.
Delta HR. And they tell it to you here, I believe. Delta H reaction. This is for the reaction that is being studied. When they say delta HR, it's the reaction that they're asking about. So this is our delta H R. And then, notice how they give you the numbers here. Take a look back at the question. They give you the combustion of carbon and the combustion of hydrogen. They give you 2 different numbers, one for combusting carbon and one for combusting hydrogen. So that actually means that you've got 2 arrows here. One to go from carbon to carbon dioxide. We call that the enthalpy of combustion of the carbon. And we've got to do the same thing to hydrogen, right? We've got to combust hydrogen. What formula does this give you? By the way, if you hate energy cycles and you don't like putting this stuff together, this formula always works for combustion. Once we put it together, you could just put it on your stuff to memorize if you prefer not making a cycle every time. How do I add these arrows together? Remember what I did last time.
Delta HF plus delta HR.
So it's going to be these 2 are going to the product, right? So I get delta HF plus delta HR, and I'm doing purple arrows to show this is the one direction. And what's the other one?
Delta HC and delta HC carbon and delta HC are hydrogen.
That's correct. So these 2 arrows are going here. So we add these 2 together. So on the other side, you get delta HC carbon plus delta HC or hydrogen. Do I have enough data to now solve? Like, do I have enough information now? They're looking for the delta HF. They've provided me the delta HC for carbon. They have provided me the delta HC for hydrogen. And they have provided me the delta HR of reaction. Take a look. So I have everything except for one.
Yes.
I have the delta HR, the delta HC for carbon, and the delta HC for hydrogen. So let's go ahead and see if we can now solve. Delta HF is what I'm looking for, right? So that's going to be still what I'm looking for. So we would call that delta HF. Does it tell us the delta HR? What is it?
Negative 1,367.2.
Kilojoules per of what?
Nuclear reaction.
It's a good question. The delta H, the enthalpy of reaction is negative 1367.3 kilojoules per mole of what?
C2H5OH.
Correct. Per mole of, it's not written in the question, but maybe you understand for yourself. How many moles are we combusting here in this overall reaction? So what would we multiply negative 1367.3 67.3 times. So technically the number's the same. So you're literally just going to see me put in negative 1367.3. Why am I making a point about this? Let's talk about carbon. The enthalpy of combustion of carbon is negative 393.5 kilojoules per mole of
Carbon.
the number here, the balanced number, right? That's why I'm bringing this up, because the moles matter once again. So I'm going to now have to do 2 times negative 393.5. I want you to have understanding of where these numbers are coming from. And then hydrogen. We have our value that says negative 285.5 kilojoules per mole of what? Hydrogen what?
H2.
Right? So what do we have to multiply that by? Looking at our data. Because there's 3 here. Which is why it's important to complete it correctly. So it would be plus 3 times negative 285.5. Now what do we do? Do math. So now you have to do the calculations. You have to add up all your products, load them back. See if you get the same thing as me, or else I'll solve it from scratch. I got delta HF minus 1367.3. And then I did all my products. I added all of this together first. Yes. Go ahead. And on my product side, I got negative 1643.5. Then I'm adding both sides 1367.3. Which is the proper algebra. If I subtract, I have to do add, right? Opposite of subtract is add. And then I get delta HF equals negative 276.2. Check to see if you get the same thing. This is the answer, actually. If you know how to put the energy cycles together, you'll always be able to create your own formula. If you hate energy cycles and they're the bane of your existence, the other option is just to memorize the two. The one for delta HF from delta HF values and the one for delta HF from delta HC values, which is what we're looking at now. I do advise to know how to put energy cycles together if you can. All right, good? I'll give some more time. It's hefty. It looks hefty. Imagine somebody just walking in the classroom without seeing chemistry. I always think about that. Somebody has never seen chemistry before and walks in this. With a triangle. Symbols. Looks crazy. Or it looks crazy without being explained. It's hard. All right, ready for the next one? Okay, I said old Cambridge question. I actually do mean older. I think this is like 10 years old, but it's still a good question. And remember, they're pulling old questions. That November 23 exam had minimum 2 or 3 questions that I know that we've covered before. All right, they tell you propanol has the molecular formula C3H6O. If you have a hard time seeing it, it is C3H6O. Could they make you know that, like yourself? Could you have figured that out yourself? Propanone is C3H6O. Yeah. Could they have just told you propanone if they wanted to do extra mean? Yeah. That's why I told you they can adjust the level of how difficult the question is. Yours? We're supposed to know propanone's this, right? CH3. Organic's not going very far away, just so you're aware. It's coming back in just 2 weeks. After we finish this unit, we're going right back. It's propanone. But to answer our question, we don't make a cycle, what would we then need to do? We'd need a formula, right? So I'm gonna just show you what that looks like without making a cycle because it's a paper one question. So do you really have to make a cycle? Would you waste your time?
No.
I would not. So it would be delta HF
Equals
plus delta
R.
HR equals all the delta HCs on the other side, right? So delta HC of the carbon and delta HC of the hydrogen. This formula works every time if given combustion values. So let's see if we can figure out what are we being asked for and where is the information. What are we being asked for, first of all?
The delta HF.
So I know I'm looking for this. That means that the other numbers they've given me have to be those other numbers. Enthalpy change of combustion of hydrogen. Do I know which of those that is?
H2.
This one, right?
Yeah.
And it was H2, right?
So
Why do we care about that?
it would be 3H2.
So we know that this is actually going to be 3 times negative 286. How do we know that it's 3 times negative 286? The standard state of hydrogen is H2.
Valid.
We have to look at this amount and see what do we have to multiply 2 by to get to 6. This is like the quick strat to solving actually without having to write everything out. So that's why I'm be careful that I don't skip steps. Try not to anybody confused about how I got 3. Alright, carbon. So I did this, check mark. Number for carbon, it says combustion of carbon, is that this or this? The one that says carbon, right? So, alright. Carbon exists single atoms. It exists as single atoms. And there's 3 of them in this molecule. So what would I have to multiply negative 394 by? Correct. Does that strategy make sense to you? You're going to just have to keep track of it. Make sure that you remember that carbon is single and hydrogen is diatomic. And it's coming from this really. Like, it's coming from this chart. You just don't have to write it. Which one? This 3. So knowing that carbon exists monotomically, we know that negative 394 is for each carbon. But in the formula propanone, there are 3. So you have to combust the amount you have, which is 3. This number is for each one, so you have to multiply by 3 because you have 3. Yes? Okay. Yes, so far? I'm still missing one number. Do we have it? So this is kind of mean, right? The enthalpy of combustion of propanone is the delta H of the entire reaction that's being studied. The reaction that we're studying is combusting propane. So that would be the missing delta H part. And so this would be negative 1786. So just change it to subtract 1786. So now see if you can solve it. Delta HF minus 1786 equals 3 times negative 394 plus 3 times negative 286. I solved it earlier. Let me know if you get the same thing. I got delta HF minus 1786 equals negative 2040. I put all this stuff together. Get that. And I got positive 1786 inside. And this gave me negative 256. Or negative 254. Which is as a response. Would I necessarily advise going for this mark on a paper 1? You have the time. And you like this math. enthalpy of combustion. What do you have to know out of this? You have to know how to make an enthalpy cycle, an energy cycle, and you have to be able to do calculations with that formula. Now we're going to go on to the main topic of the day. So that was actually the end of last class's topic. So this is the new topic. It's called bond energy. And so what do we mean by bond energy?
Like the energy in each bond.
So when we used to draw this thing called Lewis structures back in the day. We drew water. Right? This is called a bond, called a covalent bond. So what we're talking about here is the following. In a chemical reaction, we know that atoms rearrange, right? They rearrange in some manner. But for this to happen, you've actually got to break the chemical bonds. And if it's a covalent compound, you've actually got to break the covalent bonds and then rearrange and then form new bonds as a result. So when you think of combustion, if you think about what's happening, a simple combustion, like this is ethene, what's happening here? You've got some ethene, you've got oxygen gas. What has to happen to go from reactants to products? You literally have to split this bond between these two oxygens. Do you agree?
Yes.
Because these oxygens got to go to carbon, and they got to go to make water. And you've got to split these bonds between the carbons and the hydrogens and the carbon and the carbon to rearrange the atoms. Do you think that breaking bonds requires energy? If you break a bond, like let's say that you're breaking the bond, you're breaking the hydrogen off from ethene. You just go, knock that off, split it. What are you left with if you do that? Just go through this thinking exercise. What are you left with? You broke that bond. Is this stable? Is that stable? So when you break the bond, you remove your compound from a stable state. This will always require energy, and it requires a lot of it. If you look here, they're using small calories, because this is the diagram I found online, the reason we're working with calories. But 111,000 calories to break 1 mole of water bonds from the oxygen to the hydrogen. 192,000 to break CO. 82,900 to break 1 CC bond. It's a lot of energy and that's why combustion requires fire. You need something that's gonna be giving you a lot of energy. And so it's important here, and you do need to memorize this, but it's better to understand. It requires energy to break bonds because it puts you into an unstable state. And when new bonds are formed, these new bonds between carbon and oxygen, and these new bonds between oxygen and hydrogen, this actually releases energy as what you have goes to a more stable state than before. And so it's important to know requires energy. Is that endothermic or exothermic? At a point. Energy in. That's endothermic. Put that for yourself. Releases energy. Is that endothermic or exothermic? Or exothermic. Negative. These terms are coming back. And are important for this unit. You have to understand. Requires energy means energy in. Releases energy means energy out. And so what we're going to be doing with bond energies is we're going to be breaking the covalent bonds and then reforming new covalent bonds. Theoretically, but yeah. So what is the definition for bond energy? It is actually the energy needed to break a specific covalent bond, and it would be 1 mole of that covalent bond. So it is going to be in kilojoules per mole again. Yes. kilojoules per mole. You have a paper that I have passed out to you. It says bond energies at the top. I want you to write on that paper, given on exam. Given on exam. You do not have to memorize these numbers. So write it at the top, given on exam. But don't lose it, because are you going to need to use this for your homework, possibly?
Yes.
Quite possibly. These used to be part of what was included in something called a data booklet. Cambridge took away the data booklet in 2022. There no longer is a data booklet. But that doesn't mean you need to memorize these. What it means is that now they're given inside of the question itself. So whatever bond energy values are needed would be given in the question, just like before. When you're given these numbers, they give them in the question. Now they're doing the same thing with the bond energy values. However, some of the homeworks I give you are pre-2022 questions, so you'll still want to have this as needed to be able to solve questions. That's why I printed that out for you. Something important here. The bond energy values as printed are always positive. The definition of bond energy is always positive because it is defined as the energy needed to break a bond. And breaking a bond requires
More.
energy. So always positive because breaking bonds requires energy. So it's always endothermic. You're not going to have exact bond energy values, actually. In every compound, the bond energies are slightly different. So what you're going to be given are average bond energy values. These will be provided for you in any questions. So we're about to get to questions shortly. Yes.
What is P?
That's a great question. If you look at the bond energies, which I'm going to show you shortly, there's a front and a back to it. It says homonuclear versus heteronuclear. See if you're on that side. What do you think a homonuclear molecule is? Homonuclear, what do you think that means? Same atom connected to itself. So like H has to be connected to H. D has to be connected to D. N has to be connected to N. And then they give you different numbers here. I'm just rewriting what I see. And then the other version is heteronuclear, which you have HF as an example. So what's the heteronuclear?
Something bonded to a hydrogen or a carbon.
So both of these categories are diatomic,
Oh.
which means just two atoms in total in the molecule. Diatomic molecules can either be homonuclear, which means same atom connected to itself, HH, ClCl, FF, so on and so forth. Heteronuclear meaning the two atoms are connected to each other, but they are two different elements. But these are all compounds that exist. HF is a compound, HCl is a compound. To break that one bond requires 431 kilojoules of energy for every 1 mole of it. Now, you asked an excellent question. What is D? And I mean, if they want to be really spicy, they would give you D. D is something called deuterium. Anybody know what that is? It's the isotope of hydrogen. D is this. Hydrogen with a massive 2 instead of a massive 1. It's deuterium. It's a isotope of hydrogen. Do we care? Not really for what's being given here, but in the A level it would matter because it's used as a biochemical marker in advanced organic reactions to tell if a change has happened. We use heavy hydrogen in order to tell. But just so you know, it's hydrogen, just heavy hydrogen, an isotope of hydrogen. They don't print, like I said, they don't give you this whole list anymore, but you may need it in the homework. Yes. Good to move on? On the back of the paper for bond energies, you're going to see 3B. It says bond energies in polyatomic molecules. What is a polyatomic molecule versus a diatomic molecule?
Polyatomic is more than two atoms.
So you would use it if you had 3 plus atoms in the compound. So when I was talking about this, ethene, I would use the values for polyatomic molecules to solve for ethene because this has more than 2 atoms. How many atoms are here in ethene? So 6 is more than 2. So that would be polyatomic. So we can only use average values.
So add up the bonds with double bond carbon and the double and the bonds with carbon and hydrogen.
Yes. So you'd have 4 CH bonds and 1 CC bond. So that's what we're about to get to. And so the skill that we're gonna need to have going into calculations with bond energies is you're gonna have to know how to draw Lewis structures. So we're gonna go back, and that has to do with drawing display structures for organic molecules, actually. Octet rule is in play. And before we get to it, this is the formula. Unfortunately, this is a formula you technically have to memorize, but it does have reasoning behind it. If you understand how reactions happen, on your reactants, you have to break up all those bonds. This is what I was saying before. Remember when I said this? You break this bond. Well, guess what? You would also have to break this bond, and this bond, and this bond, and this bond, right? You have to break all those bonds. You have to break all the bonds of your reactants. So you have to break all those bonds, which requires an input of energy. So what you do on your reactant side is going to always be positive, an endothermic reaction. On your product side, when you form these new bonds, energy is released, which means that it's always going to be exothermic. So your bond energies for your products, you're always going to change to be negative. And so that's where this formula comes into play. The enthalpy of reaction from bond energy values is calculated by adding up the energy of all your bonds that are broken and then subtracting all of the energies of all your bonds formed. So it's actually extremely similar to the other formulas we've seen, except it ends up being reactants minus products. So I'm going to walk you through the process. This is the formula. And we're about to get to the practice questions. Ready? Here we go. So I think I've given you hopefully enough space to solve. It says the equation for the combustion of ethanol is here. A, rewrite this equation to show all the bonds. What do we mean by show all the bonds? Lewis structure. So what is the Lewis structure for C2H5OH? I'll write it up here.
Double bond C. Single bond C.
C, single bond C. H, 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 O, and H. Ethanol, right? This is the displayed formula for ethanol. 3 O2s. How do you know if oxygen is single, double, or triple bond? You just do? Well, how do you know? Oxygen has how many valence electrons? So it has to make 2 bonds to get to 8. Oxygen is always going to be double bonded to itself. It's just internalized. What number's in front there? 3. I'm rewriting the equation. Now on the product side, what do I have?
2 CO2.
You know the Lewis structure of CO2?
C with the double bond to oxygen.
You should know, right? It's C with the double bond on each side. What number's in the front?
2.
And then water, how many? And how do we write water?
HOH.
So that's it. Rewrite the equation to show all the bonds. Why do we have to do this? Part B.
So you can calculate all the energy.
So what we have to do here to calculate the enthalpy of reaction is we have to break every single one of these bonds. We break all of these CH bonds, the CC bond, the CO bond, so on and so forth. So I'm going to give you a strategy. These are all kilojoules per mole. All of these numbers are kilojoules per 1 mole. So are you going to need to know how many bonds you're breaking of each? Definitely. So let's take a look at the reactants first. Add up all the numbers on the reactant side. What type of bonds am I breaking on the reactant side? And I'm going to use a different color to notate this. What type of bond am I breaking first? Welcome back. You can just read it left to right.
There's 3 carbon-hydrogen bonds.
How many carbon-hydrogen bonds do you see on the reactant side? I'm going to go ahead and highlight them.
5.
1, 2, 3, 4, 5. Do you see them? Every one CH bond requires an energy of
410.
410. So we're going to start with CH bonds. And it's 5 times 410. Are we good with that so far?
Yes.
So 5 times 410. Man, I need to calculate.
2050.
2050 sounds right. It's not even gonna be calculated for this. 2050. All right, what's our next type of bond? On the reactant side, what do you say?
Carbon.
I'm going to go left to right, so I'm going to do CC first. So CC, I've only got one of those. Do you agree? So CC,
47.
find the number. You don't have to memorize numbers here. You just have to follow the strategy. It's going to be 347 times how many?
1.
1 times 347 is 347. All right, what's my next type of bond? Pick a different color. So let's do green. CO. C single bond O. Do I see that there?
Yes.
336. How many do I have?
1.
1 times 336 is 336. What else do I have on my reactant
All
side?
simple bonds. OH.
OH. I'm going to do that in orange. What's the number for OH?
465.
OH. 1 times
465.
465 equals 465. And what else?
That's it. Oh, no. The double bond.
Everything on my reactant side matters.
Double
What
bond.
else is on my reactant side that I'm breaking? I've broken up ethanol with all this, but I also got to break up the
Oh, double bond.
O double bond O. How many O double bond O's am I breaking? Because although it's 1 in each molecule, there's 3 of it, right? There's 3 of that molecule. It's this, this, this. That's how to understand the 3 in front, right? So 3. So it's 3 times
490.
496. And then you're supposed to add up all these numbers and get a total amount for your reactant. So then what's 2050 plus 347 plus 336 plus 465 plus 496. I get 3694. Double check my calculator. I'm going to double check myself. I did not calculate. Oh, 3 times 4. I get 4686. Let me know if you get the same. I got 4686. I correct my limit. So far, so good. So that's the energy to take apart all those bonds. Oh, what do we still have to do?
The reactant side?
We did the reactant.
The
We have to
product
do
side.
the product. So now we have to do the same process for the product side. For the products. List out what you have. Carbon dioxide. How many C double bond O's do you have on the product side? 2, but then there's a 2 in front.
So 4.
So it would be the 2 bonds there, but you've got a 2 in front, right? So that actually means if you see 2 CO2, that means you've got 2 of them. COO and COO. How many bonds are you breaking in total? 4. So for your product side, it would be CO is 4 times what number?
805.
8. Next.
HO.
How many of those do I have?
HO 6.
Correct. Because it would be 1, 2, but times 3, right? 2 times 3 is?
6.
So it would be 6 times 465. Add all those numbers up. 4 times 805 is 3220. And 6 times 465 is 2790. And then you add those 2 up, what do you get? I get 60 times. How do we get the enthalpy of reaction? So, understanding you had to break bonds for reactants and you have to form bonds to make products. Would you change the sign of either of these?
No. The
Breaking bonds means
positive.
plus. Forming new bonds means,
Negative.
and that automatically gives you what you have to do. Your answer is going to be 4686 minus 6010. And let's see what that gives us. So we're looking for the change. I get negative 1324.
Yep.
Does it make sense for an enthalpy of combustion to be largely exothermic? That's a big negative number. Does combustion release a lot of energy? Is that like it's perfect?
Yes.
Yes. You should always look for your answer for a combustion to be a large negative number. Always. Are combustions always negative?
Yeah.
Yeah. They are. All right. So this is the process. How are we feeling about it so far? Good? Oh. I don't want to go back and forth anymore. But you have another slide. All right. Here we go. Old Cambridge question. So, they give you this. What do you notice about this? Let's do this one. Do they give you the Lewis structures?
No.
Do they tell you to draw them?
No.
So is it implied that you need to know to do that?
Yes.
Yes. So you're going to draw the Lewis structure for your reactants, or the displayed formula, same thing, and the displayed formula for your products. So let's see if we can do that. CH3CHO. Oh my gosh, do we remember what that is? It's been just not that long, guys. It's an aldehyde, right? So the first reactant is this. You cannot leave organic behind. That, we're good with that. HCN. What is the bond between carbon and nitrogen always? Kind of just something you remember. H, C, triple bond, N. Always triple bond. And then product, what do you make? C, H, 3, C, H, O, H, and C triple bond N. That's what I see. It says use bond energy energies from the data booklet. Data booklet does not exist. What does that mean to us? If we're told to use bond energies from the data booklet, would you please use the printed paper I gave you? This is the question that came before 2022, yes? So numbers. None of these are diatomic elements. So switch to the side that says polyatomic to find your numbers. Be careful. Diatomic elements means literally 2 atoms. Even HCN has how many atoms? 3. Meaning that the bond of CH is affected by the fact that nitrogen is there. So do not use the diatomic, use the polyatomic molecule side. All right, so what do we do now? Time to count, right? Count your bonds. For the reactant side, what do you see first? This time I'm going to not switch my colors. So how many CH bonds do I see? 1, 2, 3, 4, 5. Actually, maybe I should use color. Do you see it? On my reactant side, remember the arrow separates your reactants from your products. 1, 2, 3, 4, 5. Just use a line just to recognize that you've counted that already, right? So then CH. What's the number for that? CH. 410. So it's going to be 410 times?
5, which is 750.
What's our next type to analyze?
DC.
See? I only see one of those. Do you agree? 1 times 350. C double bond O? One of those.
1 has 740.
Wait, let's double check that. You're right. Be careful with C double bond O with the data booklet. They give you 2 numbers. One that says C double bond O, and the other one says C double bond O in only carbon dioxide. This is not carbon dioxide, so we do use B740 here. And what else do we have? C triple bond N, which is 8 nitrogen. So now that we've got all that, we add up all our numbers for our reactants. Plus 8 nitrogen. I get 4,030. This is a number I recognize from teaching in the past. You get 4,030. Let me know if you did the same. Always track along with me. I did not solve this in advance, so I could punch a number wrong in the calculator. Double check you did the same thing. Nobody is absolutely perfect all the time. All right, are we good with reactants? So now products. This was reactants. Now we got to do the same thing for our product side. First type of bond is CH. 1, 2, 3, 4. So that's going to be 4 times.
4 times.
I just write this out to keep track for myself, but if you wrote just 4 times 410, I would get it. Next is CC. How many of those do we have? I see 2 of them. 1, 2. So CC, my number is 2 times 350. So this is 1640. This is 700. What's our next type? CO. We didn't have that before on the other side, so I have to pull the number. What's CO? Single bond O is 360. Does it make sense before moving forward that C single bond O is 360, but C double bond O is 740? The more bonds you have, the stronger bonds you have, will require more energy to break apart. So it actually turns out that triple bonds require the most energy on average, then double bonds, then single bonds actually require the least energy to break apart. Just bringing that up. That is important to know. So 1 times 360 is 360. What's next? OH. OH is, we didn't have that before, right? So that we got to figure. So it's 460.
triple bond L.
And C triple bond M, which is 890. 1 times 890, which is 890. Add up all those numbers, what do we get? I get 1640 plus 700 plus 360 plus 400 plus 890. I get do you get 450?
Yes.
I get 4050. Always double check your own math when doing this. Like, there's a lot of numbers going in the calculator, mistakes can get made. All right, how do we get the final answer? So we just got to remember, the reactants are positive because it's breaking bonds. The products are negative because you're forming bonds. If you remember that, you don't have to memorize the formula, by the way. If you remember that, then it's just technically you take the reactants, you respect the math. It's positive 4030 minus 4050. So put those two numbers together and you get negative 20. Yes. On the test next week, yes. So Cambridge is not going to make you memorize any of these values. Therefore, if I give you a pre-2022 question, I have to give you this sheet to solve, just like with the homework. Okay? And the tests are usually like a variety, as long as it's within the standards that Cambridge puts for us. Yes. Sure they will. With the numbers in this question. So the way Cambridge does it is like this, where the numbers you need are in the question. This will be on the test. It is a standard that can be assessed by Cambridge. Can I guarantee it? No. But like, it's possible. It's not out of the standard. It is in the standard. It's just the data book is no longer given. So these numbers are in the questions now. Let's take a look at this question. We're almost done. I think we're going to do, this is our last question, and I'm going to give you some work to do. And then the very last topic, I'll wait till next class, because your brains need to practice this. You do need to practice this. I don't want to overwhelm you on any one day. So here we go. Nitrogen and oxygen can react together to form nitrogen monoxide via this reaction. What is the bond energy of the bond between the atoms in NO? Consult the data booklet values to help you, but you'll notice NO is not there. So how can you figure it out? Any suggestions? They've given you this time the enthalpy of reaction, which is what we would have been solving for in all these other questions. It's off by a factor of 2. And I'll tell you why. You're doing for 2 NOs, but it's for 1 NO. Like when you do the math.
Oh.
All right. First of all, what's the first step we're supposed to do here? Draw the Lewis structure. So this would be N triple bond N plus O double bond O makes 2. What's the Lewis structure for NO? Nitrogen has how many valence electrons? 5, right? Okay, satisfy octet rule. Bond here. Bond here. You literally cannot satisfy the octet rule here. It is this. It's this. I haven't talked much about it. It's actually going to be at the beginning of organic part 2. What's that? I think I mentioned what it was.
A lone pair?
It's a lone electron. It's called a free
radical.
That means that this is a super dangerous thing that's being produced, right? Not stable, totally unstable. But apparently it doesn't happen. It doesn't stay that way very long. What? It's not very stable. nitrogen dioxide, then it goes into your water as HNO3 when it combines with water, and then acid rain and erosion with the fishes. There's a whole. Yeah. Anyways, that's what that signifies. Free radical, dangerous. But it does happen actually. This is a reaction. They're telling you this happens. So they're asking, hey guys, when we break this bond, what's the number there? Just to disregard that that's a free radical for now. What's the number when we break this bond? How will we do that? Can you come up with a strategy?
Add the numbers for products.
Do we know what this number is if we have this paper?
Yeah.
Is this a diatomic or a polyatomic molecule? So go to your diatomic side. Look for N triple bond N. What's the number? We know that this is 944. And don't we know oxygen as well? 496. And we have no clue what NO is. We're looking for it. So what do we call it? This is 2X, right? Remember, your reactants are positive and your products are negative, so you've got a formula now. This plus this minus this equals, right, so 944 plus 496 minus 2x, because its reactants are positive and products are negative, equals, well, they gave you the whole thing, is 180 in the question. So now it's simply solve for x. Do the math, solve for x. Notice that it's 2x, so you will have to divide by 2. And let's see what you come up with. I get 1440 minus 2x equals 180. Subtract 1440 by both sides. I get negative 2x equals 180 minus 1440. Which is negative 1260. I divide by negative 2 on both sides.
Oh, it's toxic.
And I get 630.
Oh, okay.
If you're asked for a bond energy value, it has to be positive. So if they give you any options that are negative, you would immediately take them out. Of course, in this question, they weren't so nice. And they didn't give you any negative choices. But bond energies have to be positive. All right, so this is going to be where we stop for the day. The very, very last application of Hess's law, I'm going to wait till next class to do. I'm actually going to give you time to work on questions in class. We are very close to being done with the unit. With the enthalpy part. There's just one type of question I have to teach you, and then we're pretty much done with enthalpy. And we're going to move on to speeds of reaction next class. It is also a math-related topic. There will be math in that topic as well. We're finishing most of the lessons through this week, and then we'll have a lab review and test next Thursday. Go.
Bad headaches daily that kind of don't go away ever. Also
Or I might tell you, you want
sometimes.
a copy I wrote on if you want this one.
Here is also sometimes.
I wrote in commentary.
They're not hard drugs. They're over the counter drugs.
That's what the pharmacist is there for.
Well, yeah, but I need my ibuprofen.
There you go. All right, so you've got some time. Go ahead and get started. Any questions? You will first.
That's for him. That's not
Yes. Thank you for reminding me.
emotionally, yes.
6 and 9 are what we're on.
Yeah. It depends on the person. It lasts 3 days to 9
It has answers to questions. I know. So I don't know. I don't have a computer that even uses that anymore. Like I can't can't use it, but if you have a computer that has a CD-ROM drive, it has answers. Okay. I'm writing your name, and I'm writing it down for me to remember that I'm lending it to you. The choices are you give it back to me at the end of this year if you're only taking AS. If you're taking A, you actually can keep it for another year.
Thank you.
Because that textbook is for both years. It's 1 through 18 for AS, and 19 through 30 for A. A has less stuff.
Do not make me. I couldn't get.
So we've done 1, 2, 3, 4, 5, 7, 10. Like periodic table stuff.
I'm not like I don't need.
We haven't done it. That's the last time. We've done some of 11 and 12. Because we've done a bunch of the stuff with like the halogen group 2, like the thermal decomposition. We've done 14. We did 15, but we stopped at the reactions. So we still have to do 15, 16, 17, 18, and which is organic part 2. And we have to do, we're doing 9 this week. 8 we're doing as our last topic. So we're more than halfway through technically. We're on a good pace. But organic part 2 is gonna be hefty. That's gonna be probably the memorization the hardest one. If you like math, you want to try to do as well as possible on this test, the one we're on right now. It's a lot of math. I believe, yeah, the pass is available. Use the purple pass.
David, you're stupid.
Yes.
You're stupid.
What?
Yes, you can take that. I was just talking to Vet about that. I'll tell you which things we
No.
if you want.
It would be mine if I see it. With what?
Like, just have
Such as.
I don't want my papers to bend.
I'm gonna grab you have a pen.
David, lift it up right now. Lift it up right now.
Here. Give it back to me.
Thank you, David.
So like that.
Doesn't matter.
So we've done. Everything.
Make it out of the folder.
It doesn't have to be hefty right now, but I'm about to get rid of the book.
Hey.
But I'm letting you know what we've done. We've done chapter 1, 2, 3, 4, 5, 7,
I know I'm telling you. If you forgot, I'm not giving you my.
we've done we've done a lot of this. We've done this. We've done some of this. Some of their uses. So I know a little bit more over here in the last one, but we actually covered.
Oh, that's out of this world secret.
Like volatility.
I'd be so proud of you.
This is in our last
I would
unit.
fold like.
We've done this.
David, I'll put it right now. I'll put it right now.
Where we're at right now is
You know that metal? Yeah. You know, what's still left?
we're actually done. It doesn't look like it. Like, look at how much we've actually done already. We have done a lot.
Not the metal, that's silver, so they know it's not gold.
The hardest unit of study is
No, if you met the best, they don't go to like, I was like, yeah, why do you have problem?
you're supposed to have 4 What?
Exactly. And I didn't even get any gold ones this year at all. Like last year, like the ones you were just now. No, like here, no, like over.
Everybody's work like different. As long as this speaks, I already know what
It's like the main.
Yeah, I know it's like the biggest one.
Yeah. Gujarati is where I come from. Gujarat. That's where I come from.
I'll tell you.
Also,
care. Tell me what? Okay.
This is my book, I'm gonna whip it out.
You know, the real way to blackmail me, it's impossible. It's like, actually, think of it, like, for me to make my grandmother visit me. I never like my grandmother.
Obviously, one, I would never, because that is way too far. Without work. And they believe you. They would. Yeah, they would.
So it's done.
And they don't put ever got it. I hope you got it. I was just like,
Oh, they help. They help.
That's how I got out of my.
They know Hindi and yeah.
That's using that first word. The one that we did at the beginning. Like, what school is it?
And then they go,
where are you?
you abandoned us.
How's he gonna feel missing this lesson? Did you say sup? Did you say